So hello everyone. In this video, we are going to cover fusion and stars. This is E5. We in the earlier chapters we have covered fission and nuclear reactors. So this is this continuation of that series in section E. So in nuclear fusion, we join two small nuclei and form a bigger, heavier one, which results in lot of energy release. Now, why there is energy release when you are joining two nuclei? Because the product nuclei out of this reaction of joining is at higher point compared to the smaller nuclei. So whenever a product nuclei has a higher binding energy per nucleon, then what we see is that we see energy to be released. Now in the case of nuclear fusion, there is a higher energy release compared to fission, because in fission, whenever there is a fission happening, the product nuclei are higher, do have higher binding energy per nucleon, but the difference is not that much. But in case of a fusion, it is much higher. So for that case, we receive very high amount of energy that is released in nuclear fusion. And nuclear fusion is the source of energy for a lot of stars and astronomical activities. Conditions for fusions are very important because those conditions are very hard to replicate on Earth. This is why we are still working on fusion reactor. It is not a reality yet, but we are making a lot of progress in nuclear reactions of fusion, and soon we will have a fusion reactor commercially available as well. But what are the conditions required for this fusion reactor? The first is the temperature. The temperature is required because if we have very high temperature of a gas confined in a space, those gas will, the particles are moving with a random kinetic energy and they will keeps on colliding with each other. Now what we want is, like, when we demand very high amount of temperature, it means the particles will collide each other with very high amount of kinetic energy. The higher the kinetic energy, the more closer those two particles can get. Now what we want is, like, because the nuclei are positively charged, most of the time the particles collide and they are getting repelled by the repulsive force of the nuclei. But if we have high enough kinetic energy, then the electrostatic repulsive force can be overcome and the particles can come within the range of the strong nuclear force, which is roughly around 10 to minus 15. So once the particles are within the range of strong nuclear force being attractive, we see that the particles getting fused together to forming a heavier element. Okay, so temperature is very important thing. Now the second requirement is the density, because when we say temperature is high, the average kinetic energy is high. When we say average, it means some particles will have higher energy, some particles will have lower energy, and we want collisions between two highly energetic ones. So to make that possibility, happen frequently, we want lot of particles to be confined in a small space. And or else what will happen? There will be one fusion, but the energy of one fusion is not enough. We want multiple fusions to be happening so that a tremendous amount of energy is released. So density is very important. So the number of nuclei per unit volume is required so that we can have frequent collision to aid the fusion reaction. Then third is the confinement time. So we require that fusion reaction should be maintained for long enough time so that we can extract the energy that we are spending for the temperature and density to be confined in a space. So we want time. We want time so that we can extract that energy, we can use that somewhere else, and the fusion reaction can be thus be self-sustainable. So to make it self-sustainable, the time, temperature, density, and confinement time, all three conditions need to be satisfied. And once this is satisfied, then we have a proper nuclear reaction of fusion happening for a long amount of time. Now, the birth of a star. The star is one of the places all the astronomical activities, the stars, different stars, and different activities like neutron star, black holes, and everything begins with how the stars evolve throughout the journey. So we start with the birth of a star. In a birth of a star, there are a few important elements. The star starts with a cloud that is called as nebula. Now the nebula is just a cloud of dust and gas which is present. Now 90% of this nebula will be hydrogen gas. Then some part of it will be helium, and then very few percentages of other heavy elements. Now this gas, the nebula, the particles are very spread out and they are moving randomly. But throughout this nebula, there will be some places where the particles are much more dense and densely packed, and the gravity is much more stronger. As we know, the gravity depends on two things: the products of masses and the distance between the masses. So wherever there is a more dense, automatically the gravity start bringing two or more particles together, and thus increasing the strength of the gravity. As the gravity at a particular location increases, we call that location, let's say, a core, the kinetic energy of the particle which are near to this core will increase because they will be strongly attracted by this gravitational force towards the core. Okay, and they keep on increasing. This keeps on building up the mass at this particular location that we are calling as a core, keeps on increasing as it is becoming more massive. More particles are attracted towards the core, and simultaneously the kinetic energy increases. Now, kinetic energy is related to the temperature of the star. So, if the temperature of the core becomes high enough that it can emit a visible light, then a protostar is formed. A protostar is like a very beginning stage of a star where the temperatures and the pressures are high enough that it can release some amount of visible light that we can start. So in a nebula that we see, there are a lot of nebula in the sky. You will find that there are a lot of shining, newly born stars which are called as protostars. Now, protostars keeps on attracting more particles towards the center and keeps on increasing the temperature and the pressure at the core. But if the pressure and temperature becomes high enough, it can ignite a nuclear fusion. And once the nuclear fusion is started, there will be outward radiation pressure. That outward radiation pressure balances out the inward gravitational pressure. Okay, and this protostar thus is converted to main sequence star. So fusion is what is the main thing that needs to be started at the core. Once the fusion starts, then the inward gravitational pressure can be balanced. So no more attraction of the particles towards the core. Rather, there is an outward radiation pressure that is balanced because of the fusion, which releases a lot of energy outwards. Now, this is just a pictorial way to say what happens over the period. So we have the dust and gas cloud. Okay, then there is a change. There is accumulation of the star. There are small dense cores, and then you can see there is a core building up star, and all the particles which are surrounding this star is what we call an accretion disk, which eventually leads to formation of planets. Now, how does stellar evolution happens further? The stellar evolution, when the star radiation pressure stops, then the fusion process ends. The fusion process ends when all the hydrogen at the core is completely fused. Now, when all the hydrogen at the core is completely fused into helium, the fusion stops, the gravity overtakes and starts crushing the core. The core becomes more dense, the temperature increases, the pressure increases, and what will happen? The conditions will be ideal for helium to fuse into carbon. So the smaller and denser core will lead to formation of helium into carbon. All the helium starts to convert into carbon, which will be a less time because let's say if I have 100 hydrogen atoms, it will be fused into 50 helium atoms. The 50 helium atoms will take less amount of time to get converted to 25 carbon atoms, like that. So whenever the fusion of heavier element happens, the radiation energy is released outward is so strong that the outer surface of the star expands like a balloon, and that expansion decreases the temperature of the outer surface because it is further away from the core, while the core is constantly being crushed by the gravity into much more denser and more powerful high temperature nuclear reactor where the fusion of the heavier elements is formed. Now, this stage keeps on continuing. Even the helium gets converted to carbon gets converted to more heavier element when it finishes. So this leads to the star swelling up and the outer surface starts cooling down a little bit, but it becomes very big. This stage is called red giant. Now, red giant is a stage where the star is very high luminous because it can be visible in the sky, and it is because of its big size, but it is very cooler in surface temperature because it is further away from its core. The core is shrinking and the outer surface is expanding. This is the main story of the star, which is very close to its death. Okay. Now, when the heavier nuclei fuses, the fusion can process. The process of fusion stops depending on what mass of the star was, because the mass of the star decides how much gravitational pressure it can exert. Okay, so if the gravitational pressure is not so strong, then helium or carbon core is the ultimate stage where the star's core stops and outer layers then spread off into a planetary nebula, and what we will see is a white dwarf. A white dwarf is formed. Now, Formation of iron is not necessary for the white dwarf. It can stop up helium or carbon core acid, but depending on the more heavier masses, if there is a star which is much more massive than our sun, then the conditions are enough to fuse heavier elements, and the iron is something that can't be fused further. So formation of iron indicates that the limit has been fusion limit has been reached, and the maximum energy has been released. So gravity takes over, and then what we get is a planetary nebula where all the outer layers are shred off, and what is remained is the white dwarf. Now, white dwarf, it can be crushed further, but if the mass is not available that much, then the electron degeneracy pressure of those electrons which are crushed together, electrons can be in a confined space, they can repel each other. So there is a limit on how much the gravity can push. If the gravity is not strong enough, the electrons will prevent uh, further crushing of the core, and that's where the white dwarf is stable. It is stable because of the electrons outward pressure is balanced by the gravitational pressure. Okay, and a white dwarf can also eventually cool down into a black dwarf because there is no energy consumed or fusion is happening. So it has to cool down by radiation over the period of time, but it will take a lot of time, uh, even more billions of years than the overall lifespan of the star. Okay, so white dwarf is very low luminous. It is small size, but it has a surface temperature that is very high. Okay, this is a stellar evolution. You can see, depending on the mass of a star, we can predict what will be the possible stages of evaluation throughout the journey. Okay, so for a heavy star that is much more massive than our sun, let's say 8 times more than massive than our sun, it can go into a stage of a red giant and a supernova, where it can fuse up to iron, and once the iron is formed, then a supernova explosion, which is much more violent than the planetary nebula, is seen, and which leads to eventually formation of either a neutron star or it can be a black hole. Okay, so neutron star is formed if it is less than 40 times the mass of our sun, and black hole is formed when it is greater than 40 times the mass of our sun. Okay, so that's just a general idea what could happen at different stages of the star depending on how much mass it has. In a neutron star, is stable. Not gravity can't rush further because of the neutron degeneracy pressure, where it is just a quantum mechanical effects that we are not going in deep like what it means, but it's just the neutrons. Protons are fused with the electrons. The gravity is so strong that the electrons are made to fuse with the protons, and everything now, every atom, every particle is converted to neutron, and a very strong, heavy core of neutron has been formed. A neutron star is so dense that even the Mount Everest can be the mass of Mount Everest can be fit into like an ice cube size uh, object. So that much how much dense the neutron star is. It looks very small, but it has very high dense uh, structure. Then a neutron star, if there is a more massive neutron star, there is a limit up to which a neutron star can have a mass. If the mass is more than that limit, then even the neutron star can get converted into a black hole. Okay, so in the HR diagram, we can see evolutionary path. What is the HR diagram? First of all, it is a luminosity versus the temperature graph. It is a decreasing temperature to the right, so 30,000, 20,000, 10K, 6K, 1K, like those. And on the left hand side, there is a ratio of luminosity, like luminosity of the star upon luminosity of the sun. And that's the reason why we can see our sun to be exactly in the middle of this graph, which has a surface temperature of roughly around 6,000 Kelvin. Now, this yellow line that I have drawn, it is a band that we called as main structure, main sequence stars. So main sequence, all the main sequence stars which have the hydrogen at the core and fusing, and they're balanced for billions of years. So these are the main sequence stars. Our star is in main sequence stage, and it will remain for much more like 6-7 billion years before it starts turning into a red giant. A red giant is then goes into planetary nebula on this diagram, and then it goes into a white dwarf stage. So that is the evolutionary path of our sun. For any heavier element, it can possibly go from a blue giant, it's like from this scale, like very much more massive, much more luminous than our sun. It can go to supergiant stage, and then it can go to a, a neutron star state. Now, neutron star being small enough, so we can see very far, but it has very high temperature, so we can draw. There is no position for a neutron star on this graph, but white dwarf is to the left bottom and the red giants and supergiants are at the top right corner. This is something that we would like to remember. Okay. Now, Chandrasekhar and Oppenheimer-Volta pyramid, this tells us how much massive a white dwarf can be. A white dwarf has a limit of 1.4 times the mass of our sun. If the white dwarf has a higher mass than 1.4 times mass of our sun, it will turn into a neutron star. Okay, by fusing the electrons into protons to form the neutrons. Now, even the neutron star has a limit. If the neutron star is much more massive than 3 times the mass of our sun, then a neutron star can be turned into a black hole. So these are the conditions that are mathematically found, and we have also referred to all the astronomical data to confirm these limits. And uh, this is where the journey or evolution of the star's death, whether it is white dwarf, whether it is neutron star, or whether it can become a black hole, that can be tested. Okay, to summarize this, we can say that if the star has a mass that is less than 0.25 times mass of our sun, then it will have a white dwarf with a helium core. If it is between 2.5, 0.255 and 8 times the mass of sun, it will have white dwarf with a carbon core. From 8 to 12, it will have white dwarf with an oxygen, neon, or magnesium core. And from 12 to 40 times the mass, it will become a neutron star. And and beyond this, it will turn into a black hole. So those are the limits. Now, how do we measure those astronomical distances? So there is very simple technique of parallax method. In this case, what we observe is like we observe a distant star, and based on the distant star position with respect to its background. So this is the background stars we have. So imagine we are observing a star in the month of January, and we see a certain background, and then once after 6 months, if you observe the same star, and we are observing another background, so we will take how much is the shift, and you applying some trigonometry, we can get the distance from this R system to the star system, next star, and that distance is usually measured in parsec. Now, parsec to light year conversion or light year to meters conversion, everything is given in your data booklet. Okay, but how do we calculate this distance in parsec? By taking a reciprocal of parallax angle, which is all most of the time given in arc second. It is a unit of angle. So angles, whenever they are small, we can have a arc second as a unit of all that. So once we get this value, we will get the distance in parsec. Now, how we can solve this kind of a problem? Now, let's say there is a luminosity, mass, parallax angle, apparent brightness, all those things are given. So what we can do here is, you can see that this star is not in a main sequence. How we can show that? Now this is something that they won't ask because this requires something that is not in syllabus right now, removed from the it was there in the previous syllabus, but it's removed. So anything related to mass of a star, they won't ask much question because that formula is not given in data booklet. It is removed from the data booklet. But these are the questions that we should be able to know how to. So for example, in parsec, we want to find the distance to a star. Now they have given us the parallax angle is 2.36 into 10 to minus 3 arc second. Now if this is given in arc second, we can get the value in parsec. Okay, we can convert this into meter if we want, but they are asking parsec, so we'll keep it in parsec. And if you want it, luminosity is given of our star is 3.83 into 10 to 26. Now luminosity of that star is 2.20630 times L naught, which is luminosity of our sun. So we can calculate the luminosity of star, and they have given the apparent brightness as well. So we can measure this and we will get this distance. Now, when we use this formula, we will get the distance in meters. But if they are asking parsec, we need to probably convert meters into parsec, and that's our final answer for this question. Okay. Suggest why are the answers in this case are different, because the the methods have certain uncertainty associated with them, and the parallax angle method only works for like few hundreds of parsec. Okay, if you have something that is beyond, and one parsec is roughly around 3 to 4 light years. If you have something that is beyond like 1,000 parsec, then there is a lot of uncertainty in the calculation that can affect our answer. Okay, then we use some other method to find out the distances to very far away objects. Okay, simply angles where a lot of things have been removed, so a lot of questions you will find which will have content from the previous level which is not there. Okay. Again, this is what we have already learned in B1, where we have learned peak wavelength, how it is related to temperature by Bain's constant, Bain's law. This is something that we can find. How we can find the ratio of radiuses, because the luminosity depends on the area of the most of the stars is 4 pi r square, and the temperature is raised to 4. So we can substitute this luminosity, temperatures are given, temperature ratios are given, and the radiuses are given. So we can cancel out all the constants, and we can get the radius of ratio for the radiuses of the both the stars. Okay, the distance is same in this scenario because distance has to be same because they are binary system. Binary systems are the stars which are orbiting each other at the specific location, so they are basically around the same distance with respect to each other. And if the distance is given, everything is given, we can find the luminosity of a particular star in terms of R star. Just divide the final answer by the luminosity of R sun, which is given in the question. So this is how the most of the questions they can ask. They can ask related HR diagram related question like plot this on the HR diagram, and based on the luminosity and the temperature, you can pick out the location. The evaluation star, like the star path, it will go from here to here. So this is like evolution path. They can ask you evolution path as well. So those are the things that I usually ask in E5. If you know all these things, then E5 is much more easier chapter. Just you have to read through stuff and you will understand most of the scenario. So thank you.